All right, so let me check the stream real quick, make sure that it's actually doing it, because I don't want to do, a couple hours worth of video in it and it not show up.
Yeah, it says it's live.
It's live. Okay, so we're kind of at the tail end of the big stuff that we need to learn. Y'all have done the heavy lifting, right? Y'all know how to add things. Y'all know how to add resistors when they're in parallel. You you know how to add them when they're in series. You know how to deal with inductive reactance. Like if I gave you inductive reactance, ooh, that's a big. What is going on there? Give me just a second. That's not how it should look. Somebody's been playing like, oh yeah, like had my boy. That's nice. Oh, that's nice right there. So if I gave you et sub L, what does that equal to? 2 pi times frequency times inductance, right? All right, if I gave you et sub C, what does that equal? Capacitive reactance, this is what we talked about in this past chapter, right? So right? All right. Now, this is a direct relationship. Like, so if one goes up, the other goes up. By having this up under here, if my frequency goes up, what does my capacitive reactance do? It goes down, right? And vice versa. All right, so you do need to know about inductive reactance because it does exist, right? When you're dealing with motors, you're dealing with coils, you're going to have some inductive reactance. When you turn a motor on the first time, it exhibits almost no resistance to that current until like it starts going. So the longer that motor is not turning, you're not providing a back voltage to suppress some of that current, so you're going to have an inrush of current. It can be 7 to 10 times the amount of current that is normally used to operate that motor. Now, what we're going to learn today, one of the main reasons that we use inductors and capacitors is for filtering, okay? So when we filter something, we could do it one of two ways, okay? We could have a coil and a resistor right there, okay? Or we could have a resistor and a coil going to ground, or we could have a capacitor and a resistor going to ground, or we could have a resistor with a capacitor going to ground, okay? Now, what does capacitors let through? They let through high frequencies a lot easier, correct? Okay, so this little network right here is providing a voltage divider, okay? And that voltage divider changes based off of the frequency that you put in it, all right? So what do you think is going to come out this side? More high frequencies than low frequencies, right? Okay, now look at this. I've got a voltage divider that changes. All right, so if I had 10 volts and I had 10 ohms and I had 10 ohms, what voltage am I getting out? 5 volts. All right, remember proportionality, like I'm going to drop the same amount of voltage across each one of those resistors, right? Okay. So imagine in this situation that this changes. As the frequency goes up, what happens to this right here? It goes down. Okay, so if I had 10 volts and 10 ohms, and then I had a resistor that was practically 0 ohms, what am I getting out?
10 volts.
Actually 0 volts, because I'm dropping all of that voltage across that 10 ohms. Okay, so what do you think's coming out of here? Like, all my high frequencies are getting grounded out right here, aren't they? They're all the high frequencies are getting ground out. So I can build a low pass filter and a high pass filter with the coil. The problem with coils is they're fairly expensive to make. There's a lot of copper in them. It's a bunch of coil wire. So if we can do, right here we had a high pass, didn't we? We let the high frequencies go through, right? Imagine this is 0 ohms and this is 10 ohms, right? The voltage divider means that I didn't drop anything across that capacitor, right? Let's draw that for a second. I've got that coming in. It's a high frequency. So it's 0 ohms right there. And then I have that resistor going to ground. That's 10 ohms. I didn't drop any of the voltage across that 0 ohms, did I? If I can make a low pass and a high pass filter with both of my components, the choice becomes, what's the best way to do that? All right, capacitors are really easy to make. They're really cheap to make, and they're really easy at getting, decent amounts of farads for a small package. Okay, like if we wanted a really inductive inductor, we need a big hunk of metal with a whole bunch of copper wrapped around it. All right, you notice that when we're building circuits, we don't really like wasting a lot of room or weight, right? Costs more to ship, costs more to build. Our calculators would be triple the size. So what I'm trying to get at is capacitors are really useful, and we use them a lot more than you would an inductor for a filter. Okay, and filtering is one of the main things that we do with RL, and RC circuits, resistor, inductor, resistor, capacitor circuits. All right, so the vast majority of what we're going to talk about from this point forward is going to be RC circuits. All right, now there's one thing that we missed in capacitors I'm going to talk about right now. Okay, when you add a coil, and y'all have all done this chapter, and it's 5 henries, and I add a coil that's 5 henries, how much total henries do I have? 10 henries. If I have a 10 Henry coil right here and a 10 Henry coil right here, what's the effective inductance right there? Yeah, 5 henries, because they add like resistors. Now, the reason they add like resistors is, think about what makes a coil, or what makes an inductor an inductor, okay? The amount of turns that you have from one point to the other, right? Pretty much how close you can get them, stuff like that, but mostly the amount of coils that you can get on there, okay? Now, what about capacitors? If I have a capacitor that's in series with another one, and I have 5 micro farads, and I have 5 microfarads, how much total capacitance do I have? Capacitors are the odd man out. Okay. What makes a capacitor is the surface area of the plates that you have by each other. Okay. How close you can get those without touching. All right. And the strength of the dielectric material in there. The strength of dielectric material just means that we can get them closer and closer together and the electrons aren't going to be able to jump. Okay? When we do this, we effectively have a plate and a plate, and we're making them farther apart. So we actually reduce the capacitance when we put them in series. Okay? What we do, so we make it farther apart, the plates farther apart, which reduces capacity. So you'd have to do 1 over what is microfarads? Whatever that is, right? Plus 1 over 5 microfarads, and then you get 2.5 microfarads. Okay? What happens when I put them together in parallel? I don't make the distance any farther, do I? But I do make the surface area bigger. Okay? So when I give you capacitors that are in series or parallel, excuse me, gotta sneeze. They act like the opposite of a resistor when you're adding up capacitances and stuff. Okay. All right. So that was one thing that I wanted to clear up. How many of you got to the signal generator, like the 555 timer, like making a buzz? Okay. What that's called is an oscillator. Okay, we've got op amps and stuff in there that you won't learn about yet. But you could think of it as we're measuring 2 voltages, and once they equal, then we do something. Cool? All right, so now let's think about the capacitor as a tank of water. Okay? Cool. All right, so we've got a flap right here. And a flap right here. Okay. So we can control when water comes in and when water comes out. All right. Now, let's say that we had something that was measuring when that got to max. Like we've just got a little switch, right? And we've got a little switch down here that whenever it gets to minimal, we can know it. Okay. Now, what we'll do is we'll connect that and connect that. All right. So when we get to max amount of water, we're going to dump it out. Okay. And then once we get to minimum, we close that gate and then we open up the water that's getting fed in up here. Okay. So we've got water pouring into here, starts filling up. Once it hits here, it opens up that gate. It starts dumping out. Okay. And then once it gets down here, it closes that gate, opens that gate, starts filling up more. Okay. That's what oscillation is. Okay. Like we've got two different states. And are y'all starting to kind of understand how we get that like back and forth? Right. All right. Now, when you used a big capacitor, what sound did you get out of that speaker? Like, it was slow, right? All right, what was happening is the speed at which that capacitor was filling up was super slow. And then it let it out. And then the speed, it let it out. Now, as you put smaller, I got to sneeze so bad, but it's one of those where I've got a lot of snot that could come out, I think. And so a sneeze ain't going to be good until I go get a paper towel. So as you put in smaller capacitors, right, it's just like having a smaller little tank right there. It fills up quicker and it empties quicker. Okay. So then, right, got faster and then got even faster. And then once it gets to about, I don't know, 50 hertz or so, like it starts turning into a tone because we recognize frequencies in our audible hearing as a note. Okay. So like as we get quicker in that little is getting closer and closer together. And then like our ear is averaging that out to be a tone. And that's what tones are. Okay. So then we were actually getting a beep out of it, what we consider a beep, when the is an audible frequency too. We just don't average it out in our ears to be like, oh, that's a, 440 hertz a note, right? So as we got smaller in the capacitors, that frequency got higher, okay? And we use this all the time. Like your watch, has an oscillator. All right. Now it's a quartz, more than likely it's a little crystal that when we put a frequency on it, or when we put a voltage on it, it shakes at a certain frequency. Okay. But a lot of times when we need a clock source, like something to keep time in a circuit, we'll use, an oscillator, not much different than this. Okay. All right. So, are y'all kind of feel like you understand kind of what that 555 was doing? It was charging up and discharging the capacitor that you put in it. Okay. And the faster it did that, the higher the frequency that tone got. What happened when you put, like, a couple of y'all put like a 5 or 10 picofarad, like a puff, one of those little ceramic, little gray or little beige looking capacitors that didn't have much capacitance? It sounded like nothing. Why? Because it got into a high enough frequency. We could have measured it on the O-scope, but it got into a high enough frequency that we couldn't hear it. Like we can hear from like, I think it's like 21 hertz to about 21K. Like as you get older, that high frequency starts to roll off. Okay. But you might have thought that it wasn't working, but it was putting out a frequency that we just couldn't hear. Okay. All right. So I want y'all to, anybody got a book?
I've got a book, but it's the digital one.
Okay. Well, I'll like one day I'm going to get rid of all paid books. Okay. Like I'm going to make it so that free PDF, like I'll write it if I can't find it. Right. But you have people talk about, the wonders of the Alexandria Library. Like what mystical knowledge could we know had it not burnt down, right? Your phone has all the information that we have right now, right? If you just learn how to use it. All right. So, the first place I look isn't my books anymore. When I graduated high school and went in and started doing community college, like the internet was a thing, but it was more of a thing that you like went home and waited for a few minutes for it to turn, to get connected, and then like you had to be sparing with it because it was so slow that you weren't really able to just get anything on a whim. So you had big libraries of, tech literature and, textbooks so that you could go find the information. Okay. And there's a lot of people in your school and that you will have that will belittle internet research. Like, I was told, you can't use Wikipedia as a source, right? And that's a good thing because anybody can write stuff on Wikipedia. But that kind of messed people up in, I shouldn't ever use Wikipedia, period. Wikipedia should not be your source, but Wikipedia is a great place to find information to then go find a primary source. Okay? Everything in there is documented, and like if somebody does put something up wrong, like within 20 minutes, somebody's going in and editing that, right? So, yes, don't take it completely at face value, but I look at Wikipedia all the time because like if I know just a piece of information, I can Google that, go read that up, get a little bit more information, maybe find some more words that I could look up. And then I take those words and I look them up, and then I go and I learn more about the information. And if I'm careful about it, I can get the right information. Okay. Like I can then use that to turn around and, Google more effectively or smarter. So let's look up RC filter. Garbage. Let me go into my network settings so I can make sure that I don't know why it remits back to this 10.11.160. I'm going to say this is 5. Like an IP address, side note, is just like your home address. Okay, it's got to be unique. All right. Your subnet mask tells me, or tells the network, what part of that is going to be unique and what part has to be the same. So that 255 says that the first part of that network address has to be the same. So that makes it so that only certain parts of your network can talk to other parts of your network, right? So anything that wants to talk on this network has to have a 10 at the beginning, okay? And then the zeros say, those can be unique. The router is the address at which, the router sits. A router is like, imagine the post office. Like you send something to my computer, you send it to the address. Well, you send it to the router first, and then the router sends it to the address. Okay. So our router for in here is 10.11.160.254. Okay. So I'll save that. Now, that'll let me talk to myself. Like y'all saw that. So it's jumping through our router, coming back, jumping through my computer, going out. Y'all can see this, right? Air server is on. So that part's working. But if I want to actually get out to the internet, what DNS is a domain name server. All right. And basically imagine this is a phone book. Okay. Like Facebook.com does not have like Facebook.com. When you put Facebook.com into a browser, it goes to its domain name server and it compares that to the actual IP address of Facebook. Okay. So a big number like 179.8.250.12 or something, I don't know what Facebook's IP address is that. We don't want to have to remember that, so we want to type in facebook.com. It goes to the domain name server and then goes. So I like to use Google's domain name server because it's easy to remember, which is 8.3/8 and 4/8 and 4/4. So now I know that it's working because y'all just saw that like Continuing Lab posted something on YouTube. Okay. Phew. I can find stuff now. All right, so if I'm writing a report, I'm not going to use this as a source, but like look down here. Like references, Horowitz and Hill, that's when they go through and they make notes. Okay, so here we go right here. What is that? Just think about what happens to what frequencies through a capacitor. High frequencies go through a capacitor real easy. So what's our high frequencies doing? They're getting grounded out, right? They're just getting shunted to ground. So this is actually a what? Is it a high pass or a low pass filter? It's a low pass because the high frequencies coming in that side and then they're shooting straight to ground. Do it. VN, like, so high frequencies would come in and then they'd get shunted straight to ground. They're grounded out. Low frequencies would go through, and this would, just imagine that this all right, so we've got a resistor and a capacitor right here. Okay, so let's imagine this is 10 ohms, and then depending on what frequency it was, that capacitor became a resistor. Okay, so we've got 10 volts right here. High frequencies, it lets it through real easy. So if we got a super high frequency, this could go down to near about 0 ohms, right? Well, we've done voltage dividers, and what are we getting out here? 0 volts, right? As that frequency goes down, the resistance goes up. At some point, it's going to equal that resistance up there, and we get 5 volts out, right? Because we got 10 ohms and 10 ohms. Now, at some point, the frequency's so low that it's like an open, like infinite resistance. Okay, so what voltage we get out? 10 volts right there. The whole, the whole voltage drops across this gap. So with a low frequency, like a super low frequency, that network right here isn't presenting any real change to it, right? Like it's letting low frequencies get through real easy, and then as high frequencies start, as you go up in frequency, it starts dumping more of those frequencies to ground. Okay, so what it looks like is this. As my frequency goes up, so we've got 0 hertz and then let's say a megahertz, okay? as my frequency goes up, what am I getting out of this network? I'm getting less and less out of it, right? Okay. Now, if I put a capacitor right here, I'm still just like making a voltage divider. The capacitor is going to act the same, right? It's letting high frequencies through. But now I've got the resistor that's going to ground, okay? So as my frequencies go up, this resistance goes down. Okay. So now instead of that 10 ohm staying the same, we've got a resistor. The one going to ground stays the same, but this one changes depending on frequency, right? So I've got that 10 volts coming in at a low frequency. This is like infinite resistance. Okay. So imagine that, it's an, let's imagine that it's a super high resistance, or that's not super high, but it's 10 times what this is, right? We're going to get 9 something volts out of here, aren't we? I'm just using proportions, as the frequency goes up, this goes down. So eventually it hits a point where it's equal, right? And I'm getting 5 volts out. And then eventually it hits a point where this is 0 ohms, right? So as the frequency goes up, this goes down and we get down to like 0 ohms. And then the whole voltage is dropped across there. So I'm getting 10 volts out of here, ain't I? Okay. So go back and look at those voltage dividers. And then use like intuition. I want to do it again. What is this? What? Yeah. What kind of filter is this?
Oh, an RC filter.
Specifically, high pass or low pass? It is a low pass, right? I want you to be confident with that, right? I want you to look at it. Don't guess anymore. Why is it a low pass? Because all the high frequencies are going to ground. Okay. What is that? It's a high pass, right? Like, all the high frequencies are getting through there pretty easy. So just think about your resistor networks, and that capacitor makes a capacitive reactance that is inversely related to your frequency. As frequency goes up, it goes down. Okay. Wouldn't it be nice to be able to know what frequency? Wait, do it. Oh, low pass.
I have him right now.
Wait. Whew. I did wrong. This right here is a ground symbol. A what?
I remember what it was, so I got it.
Okay.
Sorry about that.
Oh, you're good. All right. So, wouldn't it be nice to know what frequencies we were, starting to cut over? Y'all know that I showed you that at some point that the the two resistances were equal, that might mean something in a little bit. Okay, so you got a lot of stuff like angular and, you know, things dealing with solving the above equation yields the angular aspect equals 1 over RC. But we want to get to the frequency aspect, which is 1 over 2 pi times RC. Okay? Cool. All right. So as that resistor goes up, what happens to the frequency? Because it's on the bottom of the equation. As the capacitance goes up, what happens to that frequency? It's on the bottom also. So it goes down. Right? All right. So write down this equation right here. All right. Now, I've been doing this for 20 years, and like sometimes I'll drop a zero. Okay. So, I want to make sure that I have the correct conversions. All right. So I'll put pico, nano, micro. Let's put farad. All right. Now, a farad is a big thing. Okay. Like most of the capacitors you're going to use are going to be in the pico to micro range. But all of these equations depend on putting it in terms of either henries or farads. Okay. So when it has that big C there, 2 pi times RC, it wants it in farads. Okay. When it has that R there, it wants it in resistance. We don't have to deal with a whole lot of micro or anything in resistance, but we do need to deal with kilo and mega and stuff like that. Okay. So what you want to do is keep those in your mind. Like kilo is pretty easy. If you see 100K, you know to put 3 zeros behind that, right? Find you a good like table. Okay. Man, I don't care about you, Pinterest. No, you're not tracking me, Pinterest. I'm going to find one that's not on Pinterest. Okay, I'll show you. If you don't want something, do a negative, like a minus. Okay, and it'll knock out. So this should be easier to find. Well, I'll say that. All right, so what I'm going to do is I'm going to add that to my photos. Okay. All right, so that one takes us to micro, but we need to put it in terms of farads, right? So let's find one that actually has a farads. If I was you, like, because I'm going to let you use your phone. Not to cheat, but I need you to learn how to use it, right? So this is a really good one.
Yeah, that's the same one that I was.
Well, that one doesn't have farads.
Yeah, the code is very too.
Well, the code on a capacitor. When you get small and it's too small for them to write out like 4.7 microfarads, what they'll do is they'll do just like the resistors and they'll put like 472, which means 47 with 2 zeros, and that's in picofarads, and then you'd have to convert it up. Okay. We'll look up micro to farad.
I found a really good one.
Okay, so microfarad is 10 to the negative 6, all right? So, when
This one, it didn't have like the actual numbers, but it's conversion.
okay, cool. Like, so we're looking at 1 million microfarads equal a farad. Okay. All right. So, and if you look right here, you got 10 to the negative 10 to the negative 6, which means you're moving that decimal point 6 places. Okay. Which 1 million, you got 6 zeros. Okay. All right. So let's test our assumption. How many farads is 4.7 microfarads? Four point seven, 1, 2, 3, 4, 5, 6. Period. 0, 0, 0, 0, 0. All right, so 5 zeros and 4 7. So whenever I say the capacitor is 4.7 microfarads, that's what you need to put in your calculator. Let's test that real quick, okay? And I'm okay with you doing this now that you're past the point of, like, there's some things you need to memorize. I figure if I didn't memorize it or I didn't keep it after 20 years, no, because I'll go and get an app if I have to do this a bunch, right? Like, I still need to remember 1 over 2 pi times r times c, but remembering conversion factors when 1 0 would screw me up, right? So I'll do I'll look up a farad calculator, capacitance conversion calculator. That looks pretty good. All right, so it says enter. Oh, and that's a really good, well, that's the same one. We're going to do a microfarad. So we said 4.7 microfarads. You're not going to see a farad, okay? That'd be 1 million microfarads. That thing would kill you, okay? One, two, three, four, five zeros, okay? Cool. So I would save something like this, but you're still going to have to get it to farads. Okay. So I want y'all to get a piece of paper. And I want y'all to find the cutoff frequency for that circuit right there. Remember that cutoff frequency I need to borrow some paper. You can, or I've got some paper too.
It went blank.
The back up.
Yes, sir. You want us to get the microfarads and farads?
Yeah, so I want y'all to convert the microfarads to farads, and then I want you to put it through here, and it's going to give us a frequency that cuts off at. Okay. Mhm. Anybody get an answer yet? What'd you get?
0.00295.
Mm-mm.
Do I need to search the chart or is it just 5 zeros with 1 cent?
I would double check with the chart, but a microfarad is 1/1,000,000th of a farad. All right. I've like it's okay to use, the internet to check your work or to verify your stuff. But remember micro, million, nano, billion are 9 zeros, right? A million is 6 zeros, nano is 9, and a pico is 12. Okay. So it would be a trillion. A trillion picos is a farad. A billion nanos is a farad, and a million micros is a farad. What'd you get? I'm going to tell you it's going to be somewhere around 3 to 500 hertz. Okay. Three to 500. That sounds about right. 338.79. If you didn't get that, make sure to watch what I'm doing. Okay. All right. So we're going to convert that micro into a farad. Then we're going to multiply it by 100, which goes 1, 2, right? All right. And then we're going to take that 0.00047. Like you could multiply that, but it's going to give you this, right? And then multiply it by 6.28. What do you get there? Well, what's 2 times pi? All right. And then times 0.00047. All right. So where you got like you got 0.002 da 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 da, you got to put that 1 on top. So what happens now? You do 1 divided by that number, or you could just do the 1 over x, or the x to the negative 1, 33862. Okay. All right. So don't forget this 1 up top. Okay. Did everybody get that now? All right. Now, tell me what this cutoff frequency would be. And if you get your calculator out, I'm going to be upset. It's going to be the same cutoff frequency, right? Y'all see why that's the case? Okay, now what does this mean? That using the same components, we get the same cutoff frequency. But when we have a low pass filter, like we have right here, the frequency looks like this. Okay? And then that would be our, like, where we get half power. Now, when you look at little charts of this, it's going to be in a logarithmic scale, okay? Which uses things like power, like decibels and different things like that. And like, let's say 0 is no attenuation. A -3 decibel is half the amount of power out. Okay, like it's logarithmic. It, it's kind of strange. It's beyond the scope of what we want to talk about right now. But this cutoff frequency, where it's at half the power, right, is going to be that 338 and some change. And that's going to be in frequency or hertz. Okay. Now, what's the other going to look like? It's going to raise up, and at that halfway point, it'll be at 338.6 hertz. Okay? That cutoff frequency just tells us where it's at half power. Okay? Now, what that means is if I put these two things together, then I get something that looks like this. Okay? And that means that at this little middle frequency, this frequency right here is at that 338 hertz. Now, I could use this part of the circuit down here to go out to my tweeters. I could use this circuit right here to go out to my subs. Okay? So I put an input on both of these, and then, well, let's draw that real quick. So I have my in. I've got this weird waveform, right? Then I put it through, let's put the high pass filter up top, right? All right, so the high pass filter looks like that, right? And then I go down here, I put a low pass filter on. This little symbol right here means ground. I don't want to have to draw a bunch of wires to different places, right? I've got me a crossover circuit. Okay? So I got that weird signal. It's got low frequency and high frequency components. Okay? And then I only get the high frequency components out of that. And then I'll get the low frequency components out of the bottom. Okay? And the break off point where, both of them have 300 38 hertz in them, but there's a dip there, right? So when we're talking about EQ, like equalization, like I've got, have you ever seen a graphic equalizer? Like if I want a sound system to sound really good, got a bunch of those, right? I can go through and like, boost certain frequencies and cut certain frequencies, right? Like so that I can make it sound better. If I got too much mud, I might start cutting some, low mids. Filters are extremely important. Okay? When we've got delicate electronics that use voltage to carry information back and forth, if our power supply is all like wrecked and has a whole bunch of noise from just, like the hair dryer that your wife is using or, something, then it's going to get a lot of, spurious data. Well, we can filter that stuff out. We can filter that high frequency stuff out if we need to. Okay. So this is what we're going to do. All right. Now y'all want to know the secret why I got that 338 or how I got that 338? That's even in microfarads, right? Well, that one's not working. Okay. So what do I want you to do? I want you to be really quick at being able to get like what a cutoff frequency would be. Okay. Now, don't use the calculator until you understand what the calculator is doing. Y'all make me that deal. Okay. When I'm out in the field, I don't need to like prove to somebody that I'm the best at math. I need them to understand that I'm the best at fixing things. Okay. So if I was doing like I've got, different apps on my phone that does this. Okay. Use them. But you need to understand what they're doing before you use them. Okay? So I'm going to make a deal with you. I'm going to give you some circuits instead of giving you book work. All right? I'm going to write out some circuits. And you're going to find them without the calculator and check them with the calculator. Okay? Once you can do them with the calculator, you can use the calculator. I'll make a deal with you. Okay? Now, some of you are going to do it with just the calculator. And it's going to tick me off because what if I told you I would give you 10 of them to do in here for a quiz next Monday? That you can use this calculator, but you can't use like one of those calculators. Does that sound fair? Okay, so this is what y'all are going to do. Like the book gets a little convoluted right now when we're talking about filters. Okay, so now people are going to have to watch the video because I'm about to give y'all's y'all's homework. Okay.
Can use just a regular calculator.
Yes. All right. When I say don't use a calculator, I mean like an online calculator that's going to do all the work for you.
Okay. I just
It's very important that you understand the concept of it. I don't care about like a missing zero or something like that. Like a missing zero will screw you up. So like me personally, I can do it by hand. But I'm going to use one of those after I verify that it's giving me the right answer for time constraints, right? Because like your job isn't going to be crunching numbers, okay? Your job is going to be like trying to figure out how that circuit works. So you should be able to quickly do this, okay? Use this in a pinch, but you're probably going to have this on you, right? All right, so find a calculator, find an engineering app. But I can't let you just depend on that. I need you to understand why it's that case. Okay? Y'all feel like y'all kind of understand why the math is what it is? All right. So, number 1. A 1,000 ohms and 1 microfarad. All right, you're going on all of these. You're going to tell me the cutoff frequency. Number 2. Let's do 10 ohms and 10 nanofarads. Number 3, 100 ohms and 1,000 nanofarads. Number 4, 270 ohms and 1,000 nanofarads. Number 5, 1,000 ohms and 4.7 microfarads. All right, so that's the first 5. Tell me the cutoff frequency. All right. Number 6, draw a low pass filter that has 10 ohm resistor and I'm gonna make it easy for you because you've already got that answer up there. And tell me the cutoff frequency. Number 7, same as what's up there, but it's going to have 100 ohm, and a 470 microfarad cap. Number 8. Draw low pass. Has a 500 ohm resistor and a 10 microfarad capacitor. Then all right, so 6, 7, and 8. You're going to draw a low pass, and a high pass. I tell you what the resistor and capacitor have on them, but then find what the cutoff frequency is for it. Okay? High pass looks like this. Oh, wait. That should be high pass. I'm sorry. Uh, 6 and 7 should be low pass. 8 should be a high pass. Okay? I'm going to take a picture of that so I know what I'm looking for. Okay? 10 nanofarad. All right, let's talk about what y'all are going to do in the lab. Okay? Like some of y'all got to page 19 where you built the black box 555 test circuit, right? All right. Now what I want you to do is make sure you've got that test circuit right. All right. And then go back to like 37 or wherever. All right. So you're going to use that test circuit. Like once you prove that it works the way it should, then you're going to go back to page 37 and start working your way through 1, 2, 3, 4. All right, so you're going to do all of 37. And you're going to do all of 38 and 39. 38 and 39 don't need that black box test circuit, but leave it on your board. Okay? Because 40 and 41 all right, so what I'm going to do is the lab's going forward. We got what, 4 weeks?
About 4 weeks. As of yesterday, 4 weeks.
I'm going to give you. All right. We need to do 37, 38.
Was that included in last week's lab with this new stuff?
Because what?
This included in last week's lab, or just no stuff?
Well, last week I told you to try to get to the black box. Some of y'all have already got to the black box and did page 37 already. If you've already done it and turned it in, then just keep going. Right?
I have
Oh.
a black box, but I didn't get 37.
Okay, so this is kind of what's going to round out our stuff. Okay, like y'all are going to get a lot of stuff going on. 37, 38, 39, 40, 41 needs the black box again, right? All right, so those pages are the main of what I want out of AC. Like, some of y'all might be able to do all this in this week, and I'll bring in some extra stuff throughout. But let's give this part at least this week and next week, okay? To get in. So get as many in as you can this week, and then whatever's left I won't add too much next week. You know, I'm just going to, these are the main that I want done by the time we're done. Okay. So it might be too much to do just in this setting. So if it is, then I'm going to move it over to next week, but just start knocking these out, like taking pictures of each one as you do it. Okay. All right. Y'all have a good. Yes.
About classification.